So theorems for free was already mentioned, and the core of theorems for free is a bunch of commuting squares. Now this is a Perl, and I love Perls because often rather than having a complicated new idea, explaining an old idea in a simpler way is just a huge advance, even though we tend to value complexity rather than simplicity. I would like to see us, as I said in my talk yesterday, put more value on simplicity. So I'm excited to see a Perl, and it seems that the key idea here is instead of, right, to communicate well with other people, you don't call it a commuting square. You call it a magic square. So.
Yes. Thank you for the this wonderful introduction, because that's actually the topic of the talk. Simplicity eventually wins, but it has a cost, and it's sometimes you need to widen scope. So sometimes you are in a cage, and the thing gets is complicated, and if you open the window, okay, then it gets you get fresh air. Okay, we know that this is that things start complex and then later to become simpler as our knowledge about it improves. But we have examples in mathematics where, for instance, in trigonometry, the extension of exponentials to complex numbers makes the whole thing much more appealing and easy to. So that's the thing that we are going to do here. There is this book which was, I think, written more to be respected than to be loved, because when you read it, it's. But it has a very important message. Is that the book is about category theory, and people always read the first part and they don't read the second part. And the second part is what matters, because there is a move from categories to allegories, and this wider scope makes things more interesting and easy to cope. In functional programming, we deal with functions, but we all know this, that functions are special cases of relations. And let us see what this brings us in this talk. This talk will have an example. Actually, the example has many details, which I hope you don't mind I go through with not in much detail. But I remember this piece of conversation walking with Simon Peyton-Jones. I have a formal methods background, and my question was something like, what I find lacking in functional programming practice is formal specification. And Simon's answer was, but types are the formal specifications, aren't they? They are, but it took me 20 years to understand this, okay, fully. So the title plays with this geometric construction, square. Square has vertices, labels. Let us orient them. Now we have two paths to go from B to C, and we should be able to talk about them. In particular, we should be able to compare them. This symbol of comparison suggests some kind of set inclusion. The labels are going to be relations, and this is the magic square, okay? Where does this square comes is a semi-commutative square. This name comes from my lectures, because throughout time, eventually I started to use these squares, and they explain things a lot. I'm going to give examples about this, some of them. And then the term magic arose. Of course, I have to be specific about what inclusion means, is the normal inclusion of relations. We don't treat the relations as set of pairs. We never say the pair 0, 1 belongs to less than equal. We say 0 is less than equal than 1. So this infix notation is the natural language for relations. John loves Mary, okay? The relation is infix. And the composition of relations is what you'd expect. So the magic square is actually an abstraction, a graphical abstraction for this formula. So it hides three quantifiers. One universal quantifier and the two existential quantifiers, which are the little dots of the relational composition. In the square, in the main diagonal, you have the universally quantified variables, and the other diagonal, you have the existential ones. It's a simple formula, but it has a lot in it. So there's lots of things that we can develop. These squares compose vertically, horizontally. There is the identity square, of course. And this is very important. This is where scope widens. You can invert them. There is a converse notion. In relations, you can always swap the two elements being composed. John loves Mary. It's equivalent to Mary is loved by John. This is a passive voice in our language, which corresponds to converse. And this is the big advantage of relations. Functions, you cannot invert them. You can only invert bijections. Otherwise, you go out of the functional world. So this is the thing. The extension is this one. And also, you can these things extend them functorially. So you can promote, in the same way you have maps and F-maps in functions, you can promote relations to structural relations. There is some technical details. This is called, in that book by Fried and Skedroff, a relator. So the square expands. Any square expands through this functor. Well, it needs to be monotonic. But now, some relations fit into these two squares. So the little, the circle means converse, that passive voice. If you apply those formulas with the quantifiers and simplify, you realize that the first square here means that the relation is total, and the second square means that the relation is univocal. This is where functions live. So functions are exactly those relations that satisfy these two squares. My convention is to use uppercase letters for relations and lowercase letters for functions. Now, if a function, now we can call it, fits in these two squares, then there is this equivalence of squares, which let us trade a function and its converse. So you see that this function slides to the bottom, okay? And so this is a replacement between this f and this identity. This is called a shunting rule, and it has a lot of nice consequences on the reasoning that we can do with this stuff. So you can always, and it's also reminds, for instance, in the classroom, of these things like solving equations, passing terms to the other side of the equation, changing the sign. Here, changing the sign means changing the relation, or in this case, function, to a converse of a function. This has a number of nice consequences. Comparing functions is the same as their equality, and some patterns involving converses of functions are so simple, they get simplified, and you don't have any quantifiers at all. So the existential quantifiers go away. And this is a real big advantage in this reasoning. So a very common pattern of these magic squares involves two functions, f and g, and the vertical arrows. This means that there is a structural relationship. So the R-related inputs lead to S-related outputs. So this captures a higher order relation on functions, and it's quite interesting, this higher order relation, because it enables us to start thinking about types, as we're going to see briefly, as these exponentials. So you have a number of properties of these exponentials, and we can either use arrows or we can use the exponentials as we find more convenient. So some of these exponentials, so let us go back to the definition, some of these exponentials here may involve only functions or converses of functions. That's what I was going to show here. These are special cases of those exponentials, and in some cases you actually have those. So they are higher order relations, But in particular, they can be higher order functions, and that's what you get in this pattern. So if you converse the exponent and keep the function on the basis, then you get functions. So here you have precomposition, post-composition of a function as a special case of these exponentials. Of course, relational exponentials may involve other relational exponentials, and we write them in the way we like. So you can use arrows, or you can use exponentials. So here is an example of a higher order square, and we call them Reynolds squares because they're going to play a significant role in the application of, in the instantiation of these squares to free theorems. But if you see the shunting rule at work, it moves, then the nice rule, and you get what you would expect. R related inputs, and then another pair of inputs related by the exponent, and then the output of the two functions are related by the basis of the exponentials. Sometimes it may happen, so I'm shrinking, it may happen that the two functions in the magic square are the same, or in the Reynolds square are the same. In this case, you can abbreviate the square by writing that the function f has a relational type. So now types are becoming relations, which is actually the message of this whole thing. So you write, you see the relation R on top, the relation S at the bottom, and the function going vertically. So why not write f is a function from R to S. So R-related inputs lead to S-related outputs. And types in this view are relations. And this is a very economical way of saying things. For instance, in this case, the first example tells us that the function is monotonic. And it reads well. So the less the input, the less the output. So if you want to say that the function is periodic, what you are going to say is that, you know, adding the period to the input doesn't change anything on the output. Saying that the function is constant means that whatever happens to the input, the output does not change. So it's a very meaningful, it's easy to go. So actually this forms a category, so these relational types form a category. It's actually a category identified by plotting it a long time ago. The relational type is the Hom set, the corresponding Hom set, and it is Cartesian closed, and you have currying and uncurrying and all that. Of course, when you talk about uncurrying, you have the product of two relations, which is the tensor product. Another interesting thing that this relational view has is that relations are dangerously close to matrices. Okay, and so this evolves quite easily into the linear algebra setting. So now the rest of the talk is going to be about a special case of use of these squares, which is the free theorem. So if you have a parametric function from f of x to g of x, the free theorem essentially says that the function has this relational type. And exploring this relation type is going to tell us a lot about the function itself. Because relations are very wide. So from the empty relation to the top relation, we have a complete Boolean algebra of special cases that we can use. Now I'm going to show things not going through the details, but basically going through the spirit. So suppose you have the Haskell, the const function in Haskell, from A to B to A. How much is in this type? Well, the free theorem is just saying that const has this relation type. You have the square there, and now you can perform your reasoning graphically. For instance, let us instantiate R by the identity, and then use the equivalences between the squares, and then do the shunting square, and there we are. We get this. Now, when we look at this, we see that we don't know anything about this const function. Suppose it was called function theta. Okay, const you already know this is going to be probably want to specify a constant function. But call it theta. You don't know anything about the function. So what we have here is that for whatever s, the passive voice of const a and composed with const a is larger than that s. A relation that is larger than any other relation is the top relation. Is the largest possible. So we can say that that pattern there is the top relation. So the square captures the top relation. And this pattern, f converse composed with f, is known as the kernel of a function. And the kernel of a function is a relation that measures how injective the relation is. The larger the kernel, the less injective the function is. So we can actually say that const a is the least possible, is the least injective possible function. So it's going to be a completely non-injective function, which is actually what the constant function does. Maps everything to the same. So there is only one equivalence class in the kernel. So other examples, okay, which of course this is the standard use of the free theorem, but they can be expressed graphically. Flip is another example. Is going to be used later in my examples, and of course you can derive properties of flip using this. Now the main question of this rest of the talk is, since types are higher order squares, how much is in a type? And it is quite a lot, more than I thought 20 years ago. So the example is fold right and fold left. But I'm not talking about lists only. I want to range of the Haskell data foldable class. So I may not be talking about lists. I'm just talking about this interface in the foldable class. I know that the types are this, and let us see how far we can go knowing the type of the function only. Okay. Here is the two squares. The type in it has two squares. The first square is kind of a precondition for the second square. Here they are. Now some instances, instantiating the relations with functions, identity, and we get for the foldable class this fusion law that is proved in the Bird and Jeremy Gibbons book for finite lists. So we repeat the same thing for fold right, and one of the squares is the same, the other is not, but we are led to the fold R fusion law proved by Bird. Okay, a special case of this square is when the two functions are the same, let us call it S, and h is S of a, so S is higher order, so let us pass a parameter. And this becomes interesting because this precondition square is called, states the property of permutative. S is a permutative function. So the order of the arguments, when you have two S's, so S of X of S of A of something, you can swap X with A. And this is going to play a role in the example that I'm going to read. So this is the permutativity property that Oliveira identified. If S is associative and commutative, then it is permutative, but not the opposite. So looking at these interfaces, when does a fold left equal a fold right? So looking at the types only, the hint is that we need to flip. I'm using this tiled to. You need to flip one of the functions. And this is the best we can have. Okay. So, under what conditions are the two folds the same? Free theorems always relate to instances of the same parametric function. So maybe we can find a universal property. Well, and this is when you need to be a little bit more less general. Maybe we need this property. Maybe we need to be sure that there is an alpha and a gamma, that when you fold over those parameters, you get the identity. What does this mean? This is the reflection property. And the reflection property gives us access to the type itself. We don't know which type do we have, but we know that it has two constructors. Alpha and gamma are constructors of the type. So then then we instantiate F and E in general with these alpha and gamma constructors, and we get this implication. Now let us introduce, that Y of gamma. Let us call it Z, and drop the two XS that represent input data structures. So fold RGX is the unique solution for H in the equations given. Substitute the equations, the solution, and we gave a definition of fold R. So we get from the type of fold and this assumption that that it will have two constructors, alpha and gamma, that reflect. From the theorem alone, we get the definition. And maybe we get more, because actually we get universal property, we actually get universal property of fold R solely from the type, the parametric type. What about fold left? Well, fold left is well known that it can be represented as a higher order fold right. Let us skip the details. The details are here. The advantage of defining fold left, which we don't know anything about, as a fold R, is that we can use the universal property of fold R to find universal property of fold left, and indeed it is here. So we get universal property of fold left. So how much can we go without actually knowing the body of the function? It's quite a lot, okay? So from the type, we already have universal properties. We already have the definitions of the functions. So under what condition does this equality hold? A popular assumption is that fold left and fold right compute the same output when the binary operator is associative and E is its unit. However, here are two examples of fold left and fold right being the same, and the binary operation is not associative, and the other parameter is not the unit element. It can be any number, okay? In this example, which is a numeric number. So what's going on here? Well, we can ask fold left universal to find out the answer. So let us find under what conditions this equality holds. This is standard program calculation work. So we reach a stage where we would like to have a swap between the fold and the flipped function. So let us recall this result, the permutativity squares, and realize that if the f is permutative, then we can swap the fold rights. So we do that. Okay, we do that, and we realize that it's because of that f being permutative that the equality holds. And so finally, let us. So how can we be sure that the integer division operator is permutative? We can try and prove, but it is an if-then else. It normally is an if-then else. If something, no. Better than that, and this is the top class magic square, is the magic square that captures the Galois connections. And the interesting thing is that integer division is the upper adjoint, whose lower adjoint is multiplication. Multiplication is easy, integer division is hard. It's normally these things happen. And about multiplication, we know that it is commutative and associative. So we play this trick of using indirect equality, and we show that indeed integer division is permutative, so fold left and fold right are the same. So this is not new, knowing that permutativity is enough for fold left and fold right being the same, but Oliveira in this paper does it completely different, because he postulates it, while in this view it is an outcome of the free theorem. So simplicity eventually wins. I mean, at least in my teaching, this is going to be a process whereby these things are becoming more and more accessible, but we need to widen scope, okay? And so in 1989, this paper changed the world, at least for me, okay? At least for me. And I think that's very interesting that years pass and more things come out of this fantastic result. For instance, when you have the free theorem of a recursive function, you don't even know that it is recursive, okay? So from the type, you don't even know that it is recursive. So you can actually, for instance, for the empty relation, you get the base cases. Quite interestingly, when you instantiate with the top relation, you find the situation where the function doesn't change the topology. Okay, that changes things but keeps the topology. Very interesting stuff. So, thank you for your attention. Okay.
Right. Are there any questions?
So thanks for the talk. Yeah. So you raised the questions last, say when the fold R and foldl are equal.
Yeah.
And you give just a sufficient this is sufficient condition, right? If f this
is permutative, yes.
Is permutative, then
yes.
foldl and foldr are the same.
Yeah.
So have you thought about the sufficient necessary conditions for that?
No, I don't think it is necessary.
Yeah.
Yeah.
So this talk also, I think, also relates to the first talk today.
Yes.
In these sessions,
Yes.
I think. So I believe you know that means foldl and foldr are the same. That if and only if these functions can be represented by map and reduce.
Yes.
That means a homomorphism.
Yes.
So this if and only if.
Yeah.
So actually, I think that the sort. The merge sort is actually a sort of homomorphisms in a sense is a singleton, empty, and sort of join concatenation, right? So I'm not so sure if your theory can also derive such kind of things. You know, Jeremy gave a proof of such kind of things. Whether your squares can help to, that means derive such kind of say. People call it the third homomorphism theorem. Yeah, maybe you can do that. Yeah,
but
just comments.
But there is something here which is more general than that. I don't know what the data type is. I just know that it is a foldable data type.
Right.
So I need to shrink to lists, and
you're
then
right. I'm not so sure whether the free theorem can help for that. You're right.
Yeah. But I don't even know. Maybe it's a foldable type.
Sure.
Okay?
Yeah. Okay. Thank you very much. Yeah.
Okay. Last question.
Thanks for the great talk. You mentioned there is a connection to linear algebra. Do you want to say a few words about that?
Yes, I mean, relations and matrices are form categories, which are monoidal categories, and they share a lot in common. So actually, I would say that I mean, relations are Boolean functions. So matrices are. I would say, but that this free theorem can be generalized to matrices. So basically what the free theorem says is that because it is agnostic on the parameters, what the amount of information in the input has to flow to the output, and that information can be quantitative. I don't see a reason why it doesn't work. So that's a topic for future work to extend free theorems to the quantitative side. Yes. Yeah.
Thank you.
Okay, so we should wrap this up. I do want to point out, in the interest of truth, that the photo that you had of me was not from the year that you talked to me, nor was the photo of Simon from the year that you talked to Simon.
I'll dig the archives.
So, thanks very much.
Okay.